Okay, so I'm going to begin today by just summarizing a couple of key facts that I mentioned last week, and then afterwards give an overview of how I want to finish up today. So here's the recap. So first of all, the equation and the problem. So again, in studying this equation, we need to make a certain geometric assumption that ensures the equation is elliptic. So call it admissibility. So we assume that this underlying metric is admissible. And we want to solve the following PDE. So the kth symmetric function of the conformal Schouten tensor. So remind you of the formula here. So this is the conformal Schouten tensor. We want to basically prescribe the kth symmetric function. And for homogeneity reasons, let's take the kth root here. This is going to be equal to f e to the minus 2u. Okay. And we call this star plus. So remember, if you assume that the manifold is negative admissible, that means instead of the eigenvalues of A lying in this positive cone, if the eigenvalues of minus A lie in that cone, you get a different PDE. I won't be talking about that one today because, as I explained last time, the theory is not very well developed for that equation really at all. Okay, so key in the study of these equations are certain local estimates that I stated last time. I'm going to be using them all throughout today, so let me just write them down one last time. So these are due originally to Guan Wang, and again, another simpler version and extended by Sophie Chen. So it's basically they say if you control a one-sided bound on a ball, you control higher order derivatives on the half ball. So you can control the Hessian and the gradient on the half ball if you control, let's see, max of 1 plus e to the minus 2u on the entire ball. So if u is bound, if you have a lower bound on a solution, that bounds the derivatives up to second order, and then by the results, the basic results for fully nonlinear convex elliptic nonlinear PDE by Evans and Krylov, you get bounds for derivatives of all order. So so this implies that you can get bounds on derivatives of all orders, which depend upon the min of u. So control the min of u, control everything. That's what it boils down to. Okay, so I'll end the summary on this and begin today's lecture on this. There's this example that comes from the action of the conformal group of the sphere, which tells you that in general you should not expect an a priori lower bound because you can write down an explicit example of a sequence of solutions on the sphere for which this minimum is going to minus infinity. So just to remind you how that's set up, since I want to begin talking about that again today. So you have the map given by stereographic projection, say from the sphere minus the North Pole to Rn. So this is stereographic projection. And you consider on Rn the dilation map, so the map which sends x to alpha inverse x. And this allows you to define a whole one-parameter family of diffeomorphisms of the sphere, which turn out to be conformal. Okay, so you do projection, you dilate, and then you project back. This extends to a map of the entire sphere, which is conformal. And then, since it's conformal, if you pull back the round metric on the sphere, right, you get a metric which is conformal to the round metric. And moreover, this is the key point, the minimum will go to minus infinity as alpha goes to infinity. Okay, so, So today, just a brief overview of what I want to try to cover. So to begin with, since we know by example that you can lose a lower bound on say a sequence of solutions. We want to analyze what that tells us about the underlying geometry. Okay? So in other words, suppose we want to prove a priori bounds. If you try to, so what happens if you try to argue by contradiction? In other words, assume that you have a sequence for which the minimum is going to minus infinity. What can you say? All right. So this falls under blowup analysis, and that's how we'll start today. So. And what blowup analysis gives you ultimately are solutions on Euclidean space, depending upon your blowup process. So we'll have to talk a little bit about entire solutions. It's pretty easy to summarize what's known there. And then finally, using these the facts we'll assemble here, then I'll begin to talk about an honest existence result. So this still falls under the category of general technical tools. But then I'll concentrate on a special case, the four-dimensional case, and give an existence result. So it'll be more or less a complete result up to one theorem that I'll ask you to take my word for. But I think in the second part, the second hour, I'll come back and I'll sketch out a proof of that result because it's actually pretty easy to understand. All right? So more or less, if you take the local estimates for granted and some other technical things in here, you'll basically see a sketch of the four-dimensional case. Well, okay, to be a little more careful here, I'm going to concentrate on the k equals 2 case and then indicate how k equals 3 and k equals 4 more or less follows from this case. All right. And then I'll end with geometric application. Which, on the one hand, is at least in its statement, it's a little bit special to 4 dimensions, but it turns out that people have generalized this to other settings as well. So, okay. So let's start with blowup analysis. Okay, so on the one hand, I'm going to do things a little bit carefully here, so it's going to look like it's a bit special to this equation, but in fact, what's being done here is used to analyze all kinds of PDEs. Essentially, you isolate some dilation structure of your equation and exploit that to understand what happens if you lose a certain bound. All right, so there's sometimes it's quite general what's being done here. Okay, so back to these maps of the sphere. So psi is stereographic projection. So as I mentioned, it's conformal. So if you pull back the round metric on the sphere, so G naught is always the round metric on the sphere. So round metric, you get some conformal factor times the flat Euclidean metric. So this is the flat Euclidean metric. And you can compute what this is. So u of x is equal to log 1 plus x squared over 2. Okay, now since since u is obtained by this pullback, all right, obviously u is going to be a solution of our equation, right? You're just pulling back the round metric of the sphere, so the curvature is going to be the same, right? So it'll be a solution of this equation with f equaling a constant. So u satisfies the equation with the background metric being flat, so there's no leading term there for the background curvature, right? So you get this. Kth root equals whatever the constant is on the sphere. So it's some expression involving n choose k, and so it doesn't really matter what it is. Okay, so let's write down what the dilation structure is. I mean, I've already indicated that's exactly what you use in order to write down this family here. All right, but let me state it a little more concretely. So you begin with this solution u, okay? Then you can define another solution, u sub epsilon of x, which is u of epsilon x plus log 1 over epsilon. So here epsilon positive. Think of it being, say, a small number. Now, okay, you can use the formula for u and see exactly what this is. It doesn't really matter. It's log 1 plus epsilon squared x squared over 2 epsilon. All right, so this is also going to be a solution of the equation. Why? Well, there's two ways to see this. One is, of course, just plug in the explicit formula you have here and you can check. But the other way, the better way to do it is just think about the dilation structure. So what happens is, if I check to see if u epsilon is a solution, here's the Hessian. So when I differentiate twice, I'll get a factor of epsilon squared out. These terms are quadratic in the first derivative, so each first derivative will have one factor of epsilon, but this is all quadratic. So I'll have a factor of epsilon squared coming from the left-hand side, and then because of this logarithmic term, when I exponentiate the right-hand side, I get another factor of epsilon squared. So both sides scale the same way, and therefore solutions are invariant under this kind of dilation structure. Okay. So u epsilon is also a solution. Okay, so this is just another way of, instead of pulling things back up to the sphere and writing down this family, it amounts to just, what I'm doing here is just looking at what happens when you pull to Rn and do the dilations. All right. Now, this invariance is exactly, of course, what gets you in trouble, which in other words, this is the example that allows you to create the sequence on the sphere. But this dilation structure is also going to help us out when we analyze, in general, what goes wrong for a given sequence of solutions on a manifold. So, in other words, if you have a sequence of solutions for which lower bound fails, this dilation structure will help us understand exactly what's going on, at least on a microscopic level. All right, so let me talk about that now. So I'll keep this. I think I'll keep that, in fact. Okay, so let's assume that we have a sequence of solutions to our equation star plus, so this equation here. And as we see here, again, to repeat, we just have to worry about whether UK has a uniform lower bound. Okay, so suppose it doesn't. So let's assume that the minimum of UK goes to minus infinity as k goes to infinity. All right, now to simplify some things, all right, if you have a sequence, then you can take a point at which u attains its minimum, and of course that point will vary, right, depending upon the value of k. But eventually you can take a subsequence and assume it converges to some given point on the manifold. But to simplify, let's just assume it's all happening at the same point. I mean, you can basically accomplish this by choosing local coordinates and just translate. But anyway, let's just assume that this is happening at a fixed point in the manifold. All right, so let's assume that it's all happening at some point O. And what I want to do is identify this point with the origin in Rn by introducing normal coordinates. Okay. So, i.e., assume that the min happens at a point which is identified with the origin in Rn. Let's say after introducing normal coordinates. At the point, all right? Oops. Okay, so for all practical purposes, we're imagining our sequence of solutions live in, say, the unit ball of Rn. All right, all we really care right now is what's happening near the point where u attains its minimum. So there's the unit ball. The minimum of UK is happening here. So we have the sequence of metrics. Now, G, we choose normal coordinates. So we assume that locally we can write G in this way. All right, so ij, where the components of G are big O of x squared. All right, so the coordinate system is normal. Okay, now we're going to use this dilation structure, right? So we're going to let UK tilde of x be UK of epsilon kx plus log 1 over epsilon k, where epsilon k now is e to the minimum value of u. In other words, u, it's 0. And that's going to 0 as k goes to infinity by assumption, right? Okay. So let's write down what we know about this new sequence, UK tilde. All right, the first fact is that UK is just defined on the unit ball here, but UK tilde, because of this dilation factor here, is defined on the ball of radius 1 over epsilon k, right? So UK tilde defined on the ball of radius 1 over epsilon k. So on the other hand, what's the minimum of UK tilde? Well, it's just UK evaluated at this point plus some constant, right? So the minimum is still going to be attained at the origin, and the epsilon k is precisely chosen so that at the origin UK tilde is 0. So UK tilde is greater than UK tilde at the origin, which is 0. And finally, UK tilde satisfies. All right, the same equation after you take into account using dilated coordinates. All right, so I'll write this down. I mean, if you're unfamiliar with this kind of argument, you can almost pretend you're dealing with a sequence on Euclidean space. There's some correction terms that have to be introduced because of you're doing this conformal sum fixed metric G rather than the flat metric, but they all end up scaling out in a limit anyway. So in any case, here's the equation. And I want to write it down only really because of the last term on the right-hand side. So is equal to f at epsilon kx, right? So at the dilated point times e to the minus 2 UK tilde. Okay, so where G tilde k, this is just the metric and dilated coordinates, so it's G of epsilon kx. So component-wise, it's Gij epsilon kx dxi dxj. Okay, so this metric, because we're doing this in normal coordinates, this is just converging basically to a Kronecker delta, right? So in the limit, what's happening is this is just approaching 0, right? GK tilde is approaching the Euclidean metric, which is flat, so that term will go away. So if you could take a limit here in this equation, what you'll get in the limit is exactly a solution of our equation on Rn. Okay, but the point is that we can take a limit because we've done this dilation to give ourselves a lower bound. It's a solution of our equation, so the local estimates apply. Right? So we can just apply these local estimates. U tilde has a lower bound, so this right-hand side is bounded. And therefore, we have bounds up to, on derivatives up to order 2. But then we know from the general theory that gives us bounds on derivatives of all orders. So we can extract a convergent subsequence. OK. Yeah?
What is the goal of this session?
That's a cruel question to ask. So I'm going to explain that the limiting equation can be classified. The limiting solution can be classified. So therefore, if you know exactly what the limiting solution looks like, then for the original sequence, on a very small scale, you know exactly what a solution looks like. Okay? And that's going to be very important when we talk about existence. Right? If I did this dilation argument, and I got a limit that I didn't understand, if I could only say, well, you get some solution on Rn, but I have no idea what it is, then it would almost be impossible to say anything useful about the original sequence of equations. It's precisely because, I'll get to this in a minute, we can classify these solutions. That'll help us ultimately in the general existence theory. Okay, so the local estimates imply that UK tilde converges, say in CM alpha log to some limiting solution U. And again, to emphasize, this is going to converge to a constant, right? So f is some fixed function, so you get a constant on the right-hand side. So you get a solution of the sigma k equation with a constant there. So U bar satisfies our solution with f equal to a constant. Okay, so then this leads to the question, do we know what this limit is? And the answer is yes. Okay. So that leads us to the next topic, but it's not really much of a separate topic since you can summarize it pretty quickly. So classification of entire solutions. So should mention that when k equals 1, this goes back quite a ways. So to make it a little more familiar, if you write your conformal factor using power notation instead of exponential notation, so this way, then this equation, star plus, just becomes Laplace v plus some constant v to the magical power here. Let's say U bar, since we're talking about this particular solution. And then it's a result of Caffarelli. Okay, so I guess I won't get around this. There are two F's in Caffarelli? Gita Spruck, which says that solutions of this equation are precisely given by pullbacks of the round metric on the sphere. So V up to dilation, you can always do this dilation, and you can always translate, of course. So up to dilation and translation. Are given by pullbacks of the round metric by stereographic projection. So given by pullbacks of round metric. Okay, and now there's actually earlier result of Obata, which says that if you assume a certain growth at infinity, certain decay, writing it this way, certain decay at infinity, then you get the same result. Now, for the sigma k equations, essentially same result holds. So for k greater than or equal to 2, well, when k equals 2, so this special case was covered a while back by myself with Alice Chang and Paul Yang, but much more generally, k greater than or equal to 2, and equal 4, I should say. This is special, again, 4 dimensions. But in, for any k in any dimension, Yan Li and a student Aobing Li proved the similar result. So if you have a solution of this equation on Euclidean space, all right, with f equals a constant, then up to translation and dilation, it's obtained by pulling back the round metric on the sphere. Okay, so now we're basically, this brings us to where, I mean, our state of knowledge at this point is pretty much what it is for the scalar curvature equation. Blow-ups are standard bubbles. You know what they look like at a microscopic level. All right. Okay. So now I want to start talking about the 4-dimensional case with the intention of trying to give an existence result. So let me start there. So everything is pretty much set up to reduce it down to one question. So let me begin doing that. Excuse me, get organized here. Okay, so the n equals 4 case. Okay, and as I mentioned, I'll concentrate on k equals 2. All right, the algebra is a little bit easier, and it's also easier to explain the key result that this is going to rely on. And then afterwards, I'll indicate the cases with k greater than or equal to 3. So. I say similar, but that's actually kind of pretty misleading, but you'll see what I mean by that later. Okay, so the setup, exactly as we described. You have a sequence of solutions. Right? You want to prove a priori estimates, and then what I've completely avoided last week, and I'll continue to do so this week, is any mention of how you go from estimates to existence via a degree theory argument. That takes a while to set up, and it doesn't seem to say too much. So take my word for it that once you have the estimates, you do get existence. Okay, so you have a sequence of solutions. To our equation with k equals 2. And again, we want to try to prove a priori bounds, so let's assume they don't hold. So assume the minimum is going to minus infinity. Okay, then we go through this dilation argument. All right, we blow up to get a standard solution. So as before, we dilate to obtain a solution U bar on R4. Okay. Now, you can, by adding a constant, you can normalize the solution. So let's do that. So let's normalize. Okay. What's going to be special about 4? Let me think of a precise way to state it. Yeah, okay. So in any dimension, on any manifold, you can do this blow-up process, and you get a solution on Rn, okay? In 4 dimensions, when looking at k equals 2, when you get this limiting solution on R4, you can use this in a very immediate way to go back to the original sequence, all right, the non-dilated sequence, and say that that manifold had to be the sphere, and your sequence had to be a sequence in a fixed conformal class, in the round metric, in the conformal class of the round metric on the sphere. Right? You see that rather clearly in this case. For other, higher dimensions, in other cases, you have to argue in a more global and direct way to see this. But in 4 dimensions, again, with k equals 2, it's I don't want to say it's immediate, but it's much easier to see.
It's only k equals 2.
K equals 2, but it turns out that for k equals 3 and 4, if you even though you have to check some things and change some things, the outline is there in your mind once you see it for k equals 2. Right? I'll explain that. There's something the conformal invariance of the integral of sigma 2 is used in a crucial way here. All right? And for 3 and 4, you cannot rely on conformal invariance, but there's still some comparison argument you can use and reduce it in some sense to that. Okay, so what we want to do is we want to normalize we know that our solution on R4 here is just the round metric on the sphere pulled back. All right. And maybe up to scaling, I guess I should have said here. But in any case, scale it in such a way that all the constants match that of the sphere. So we have a solution of sigma 2 Hessian u bar plus d bar d bar. So equals the constant on S2, S4 times e to the minus 2 u bar. Okay. Okay, so again, by our classification result, we know exactly, we can write down this, we can write down u bar explicitly, again, up to translation and dilation. But the key fact here is that we know that if you integrate, so let's write, so let me write it this way. So we know that g bar, which is e to the minus 2 u bar times the flat metric, that's got to be the pullback of the round metric on the sphere. All right? So therefore, we know the exact value of the integral of sigma 2. So hence, if you integrate sigma 2 for this metric, it has to be exactly equal to the sphere value. So whatever it is on the round metric times the volume of S4. And if you compute that, you'll see that it's what I always get, depends how you normalize everything, it's 4 pi squared. All right, so we know exactly what this value is equal to. Okay, but once you know that, you go back to the original sequence. So what we want to say is that on the original manifold, the integral of sigma 2 has to be at least that large. Right? I mean, this is kind of clear to see when you think about it, but I'll write down some details. So here's your original manifold. Okay? And what we did in this blow-up argument, we said, okay, suppose the minimum is going to minus infinity. Again, imagine it happening in a fixed point. We looked at a small ball and we dilated it. Right? And in the limit, as you look at the limit of those dilations, you know that the value of the integral of sigma 2 is 4 pi squared. So if the integral of sigma 2 inside this ball is about 4 pi squared, the integral of the entire manifold has to be at least that big. So it follows very, very obviously that the integral of sigma 2 on the entire thing has to be at least 4 pi squared. So a little more clearly, so if you go back to the original sequence, so gk, which was e to the minus 2 uk times g, then if you look on that, then if you integrate over the entire manifold, sigma 2 of a gk, this has to be at least as big as the integral on the ball that we dilated. This is sigma 2, excuse me. And this is just the dilated one, right? So this is sigma 2 of gk bar, so the dilated one. I guess I call it tilde. I don't remember if I called it tilde bar or what I called it. But anyway, the dilated metric you get. And this is basically 4 pi squared plus little o1. Okay. So this had to be at least 4 pi squared, but by conformal invariance, and this is key, this means your background metric, g, the integral of sigma 2 for that one, must be at least 4 pi squared. Okay. So everything will then hinge on the following result, which says that this can only happen if your manifold is conformally equivalent to the sphere, right, naturally. So theorem. By the way, this result, as it was originally proved, had nothing to do with sigma 2. It had to do with some higher order elliptic problem. So it was only after the fact that we realized that it's useful for this problem. So in any case, the statement is the following. So assume you have a manifold for which the scalar curvature is non-negative, and the integral of sigma 2. Well, actually, I just need one assumption. I'm conflating two things here. Just a second. So just assume this. Then the integral is less than or equal to 4 pi squared. And equality occurs if and only if the manifold is conformally equivalent to the sphere with round metric. Okay. So you have a four manifold, closed four manifold, non-negative scalar curvature. Then the integral of sigma 2 is always less than or equal to the corresponding value on this four sphere. And equality happens if and only if it's conformally equivalent to the four sphere. Now, I just want to mention, this is not so obvious. Nowhere in this proof is positive mass used. All right, so the corresponding thing for the Imabi, where you try to say compare the Imabi invariant to that of sphere. The hard part is distinguishing the case of equality. So in this case, so positive mass theorem is not needed to prove this. So I'll come back to this theorem later on and just give an indication of why you get to avoid using positive mass. If you use positive mass, then the statement is really almost immediate. But if you want to avoid it, it just takes a little bit more work. But it can be done. OK, so that basically wraps everything up. Let me just summarize then what that tells you. So we now know that if you lose a lower bound, then you have to be conformally equivalent to the sphere. So conclusion. If UK is a sequence of solutions to star plus. So again, we've specialized to. Yeah.
Is that supposed to be just a pedagogical logic whatsoever? Anyway, is it that the positive mass conjecture is known? So why are you?
What I'm saying is, even if you didn't know if it were true, you could still prove this.
Okay, so
Yeah.
that's just a comment.
Just a comment, yeah.
So this theorem you're saying is an immediate consequence of that?
If you quote positive mass, then this will follow. I mean, I'm being very indirect.
Presenting it this way.
Yeah. Sorry?
So why are you presenting it as such? Is it just look, I don't need that, or in fact this will be an important point?
I guess both. So I'm trying to say that, okay, when I come back to this, you'll see that this really boils down to looking at the Imabi problem carefully. And what I'm trying to say is the fully nonlinear problem does not get reduced to the k equals 1 case because you get to bypass this fundamental result. All right? So there's some underlying reason why you get to avoid.
So in a sense, this quantity is also a different way of measure the mass. That's what he's saying.
I'm just getting confused about in terms of proving this theorem.
Well, okay, let me put it this way. Yeah. What you can prove, and I'll when I come back, I probably shouldn't have said this until I started talking about the proof, but what you can actually prove is that this is less than or equal to, so how do I put this? There's a normalizing constant here, but this integral, assuming the scalar curvature is positive, this integral is always less than or equal to some constant you could write down times the square of the Yamabe invariant. Okay, so by Aubin's result, you know that the Yamabe invariant is less than or equal to its value in the sphere. So therefore, this inequality here is straightforward if you take Aubin's inequality for granted. Now the question is, what about equality? Suppose you have equality. Okay, then you're asking in 4 dimensions, when do I know that the Yamabe invariant is equal to the Yamabe invariant of the sphere? If you rely on all the machinery of the Yamabe problem, in particular the solution which eventually evokes positive mass, then you know that happens if and only if you're conformally equivalent to the sphere. What I'm saying is, but for this statement, you can bypass that statement about equality of Yamabe invariants. All right, there's a way to get around that.
So right now it's just a point that the proof can be made to avoid that.
Yeah, exactly. Yeah, exactly.
Well, that's again to be a point that, well, we don't have an analog of positive mass, yeah, hence this isn't equal to that.
Well, that's another way to say it. Yeah, we don't. Yeah, that's actually a good question. Is what is the mass for these problems? Okay, yeah. So you have a sequence of solutions to our equation, and again, we're assuming k equals 2, and we're in 4 dimensions. Okay, I'll get back to the 3 and k equals 3 and 4 later. Then you know that we have a. Well, let me state it this way. And if your underlying manifold is not conformally equivalent to the round sphere, then you have a universal lower bound, okay, for the sequence. Okay, again, the estimates tell you you control derivatives now, but let me make one more comment. So I bypassed this before because it's not that important, but okay. So if you have a lower bound on U, then you bound the Hessian and the gradient, but in principle you have to worry about, okay, I know that solutions are bounded from below, but what's to prevent them from just uniformly going to plus infinity, right? How do you rule that out? Well, it's just an elementary application of the maximum principle. You can just check. You write down your equation. You evaluate it at the minimum point of your solution. So if you evaluate the minimum point, this is positive semi-definite. These are 0. They drop out, and you use the fact that the Schouten tensor is in the positive k cone. All right. So you're using an essential way this ellipticity condition. Then you can see that the minimum of U is bounded. The minimum of U is bounded above. Okay. So just want to state that the maximum principle implies that the minimum of UK is also bounded above. So you have uniform. You have an L infinity bound. Local estimates now give you bounds up to the second order. So now you have bounds on derivatives of all orders. So you can now bound as many derivatives as you like. Okay. So that's the end of the story for k equals 2, n equals 4, again up to this fact here. Okay, but let me get organized here. Sorry. I wanted to say something about. Yeah, a couple remarks about the 3 and 4 case. So maybe, would this be a good time to take a break and then come back? Okay, well, why don't we do that? Why don't we take a 10-minute break and I'll come back and then I'll talk about the k equals 3 and k equals 4 case and explain what you have to change. All right. Yeah. start again. Okay. Okay, so let me begin with a few remarks on the proof, and in particular say a couple words about the k equals 3 and 4 cases. So you go through the argument at the beginning just the same, and you're getting limiting metric, just as you did before, on R4. And you know it's the round metric of the sphere pulled back, and you can normalize it. Okay. On R4, let's say comma, with, after normalizing perhaps, the integral of sigma k of ag bar dg bar is equal to the value on S4. So sigma k of S4 times the volume of S4. Okay, now if you try to apply the same argument that you did for sigma 2, the problem you run into is that the integral of sigma 3 or sigma 4 is not conformally invariant. So that argument needs to be modified in some way. So, but integral of sigma k greater than equal to 3 is not conformally invariant. Okay, so you need to somehow change how you argue, but essentially it gets reduced to the k equals 2 case once you do that. So let me just mention how you set this up, although I won't fill in the details, and then mention how this indicates what's going on in higher dimensions with large values of k. Okay, so in any case, so one way to get around this lack of conformal invariance is the following. So you introduce a different kind of conformal invariant. So for example, this notion called the maximal volume. So this is something that Jeff Yakovsky and I did. This works well in 4 dimensions where you can compare things back to sigma 2, but in higher dimensions it's not, doesn't seem to be as easy to compute. So the idea here is you just want to reduce to the k equals 2 case. So the basic idea is the following. You define the following invariant of a conformal class. All right, you take the sup of the volume of all conformal metrics in that class which satisfy the following. So gk is a conformal metric. gk is admissible. And you normalize the sigma k curvature of g hat to be at least equal to the sigma k curvature on S4. Okay, now if k is bigger than half the dimension, all right, then as I mentioned last week, then the Ricci curvature of g hat will be positive, and with this normalization, the Ricci curvature will have a strict positive lower bound, so the volume will have a fixed upper bound. So this sup is finite. Okay, but in fact, in 4 dimensions, you can estimate it sharply. So lambda 3 is less than or equal to, so lambda 3 and, well, actually, let me say it this way. Lambda k is less than or equal to the volume of S4 for k equals 2, 3, and 4. So you can estimate this maximal volume sharply. And equality holds if and only if M is S4 conformally. Okay. So what you do is you basically replace this integral of sigma 2 as your conformal invariant, and with this idea of maximal volume, you go through the same kind of argument and you show that the maximal volume of your underlying manifold has to be equal to the volume of the sphere, and then you use this characterization. But this characterization is really just a rephrasing of the characterization for the integral of sigma 2. So everything gets reduced to the case k equals 2, but you have to set up, but what you need to do is be able to write down some conformal invariant which allows you to run that argument that was used in the blowup argument. Okay. So I'm sorry, it's very sketchy, but the idea is to somehow impose conformal invariance into the problem at some level. Okay, now on the other hand, this is pretty special to 4 dimensions. Let me also mention that the k equals 3 and k equals 4, those are special cases, the more general problem of understanding what happens when k is bigger than half the dimension. So in higher dimensions, this notion of maximal volume hasn't really yielded much. So you have to argue differently. So let me just mention two results. So the first one, so for k greater than half the dimension, so you get a similar result. So if you have a sequence of solutions, then you get the same result. Then if Mn is different from the sphere, you get a lower bound a priori. And then let me mention the remarkable result of Trudinger and Wang. So our result, you use the fact that you're actually working with solutions. So UK are actually solutions, but they prove a Harnack inequality. Which only uses the cone condition. So if G hat is admissible, so again, just to emphasize, the results I'm talking about here only work for k greater than half the dimension. Okay, and the key point is that you get some control on the volume of a conformal metric in that case. That's key to these results. All right, then you get a Harnack inequality. It says that if, again, your manifold is not conformally the sphere, then the max is controlled by the min. Okay. Now, let me go back to the sharp result, which says that the integral of sigma 2 is bounded by the integral of sigma 2 in the sphere, and talk a little bit about that. Okay, so the theorem is if the scalar curvature is non-negative, then, so again, this is 4-dimensional result. Okay. Then the integral of sigma 2 is bounded by its value on the 4 sphere. And equality if and only if your manifold is conformally around a sphere. Okay, so I mentioned in response to Peter's question why the inequality is actually pretty straightforward. It's characterizing the case of equality that takes a little more work. So let me give a little more detail. Although the setup is pretty easy, but if I give some details, then it's much easier to see how you treat the case of equality. So the setup is what you do is you look at the Yamabe problem.
You should comment using positive mass in 16
It'll be easier if I sketch the proof, and then a few lines in, you'll see that it follows from that. Yeah. So yeah, just bear with me, and then things hopefully become more transparent. Okay. So what we're going to do is write down if you write down the formula for sigma 2, then this inequality is almost algebraic. Okay, it's almost algebraic. Okay, so I want to do that, but what you need to do is, since this is conformally invariant, you want to test it on a certain conformal metric. Now, so maybe I'll take Alice's advice and just do this. So let's just assume that let's just assume the solution of the Yamabe problem. Every conformal class admits a minimizer for the Yamabe quotient. All right. Since this is conformally invariant, I can just plug in the Yamabe metric, or a Yamabe metric in case it's not unique, and just test this value. then I'll write down the algebra here in a second. You'll get that this is less than or equal to some constant times the square of the Yamabe invariant. Then, as I said before, you use Aubin's inequality. That's less than the value on the sphere, and so this inequality is rather automatic. So let me do that. So let's write the following. Let me give myself some more room here. So sigma 2 is minus 1/2 the norm squared of A plus 1/2 the trace of A squared. So let A naught be the trace-free part of the Schouten tensor. So you take the Schouten tensor and subtract its trace. So we're in 4 dimensions, so put a 1/4 there. All right. And this is minus 1/2 the trace-free part of the Schouten tensor squared. And then let's see, minus 4 plus 4, that's 8. That's plus 3/8 sigma 1 squared. So I can drop this since it's negative, right? And then I use the fact that that the scalar curvature, well, that sigma 1, the trace of the Schouten tensor is the scalar curvature in 4 dimensions, the scalar curvature over 6. Okay? So this will be less than or equal to, let me get the constant right here, 1/96 if I got it right. The scalar curvature squared. Right? So therefore, the integral of sigma 2 is always less than or equal to 1/96, the integral scalar curvature squared. Okay, so I apply this inequality for a Yamabe metric, all right? And what I get, so and we use Aubin's estimate. And what you get is exactly that the integral of sigma 2 is always less than or equal to 4 pi squared. Okay? So as I said, it's up to using Aubin's estimate, it's algebraic. Okay, now, what if you have equality? Okay, well, all right, now again, if you use positive mass, equality, you know that equality will hold. That is to say, your Yamabe, so let me write it this way. This is less than or equal to 1/96, the Yamabe invariant squared. Now use Aubin here. This is 4 pi squared. Okay. So now if you have equality, that says that your Yamabe invariant has to be equal to the Yamabe invariant of the sphere. And okay, so that's characterized by the sphere, right? So that's where positive mass would come in. Okay, so the claim is, though, you can bypass that. So how do you bypass it? Okay, so maybe I'll not fill in any details and just talk through it for a second. What you do is you do the typical subcritical regularization of the Yamabe problem. So in other words, you look at the usual Yamabe functional with subcritical power here. So n equals, this is in 4 dimensions, so what is this? 4, right? So you look at the subcritical one where you drop the exponent. You can solve this one, right? Take this defines a conformal metric, which you then plug in to this inequality, right? And then you run epsilon down to 0. So what happens? In the case of equality, all right? In the case of equality, what happens for that sequence, so for each epsilon you solve, you get a solution u epsilon squared times your background metric. So you apply this inequality to this sequence. So if you're approaching if the integral of sigma 2 is approaching 4 pi squared, what you check after going through all the inequalities that you have, you check that the trace-free Ricci tensor, trace-free Schouten tensor, of this sequence of metrics is going to 0 in an L2 sense. And that's good enough to conclude that the underlying manifold has to be the sphere. All right, so a better way to say it is after you analyze the proof, what you end up seeing is that you can get away with an extremely weak form of the positive mass theorem. In other words, all you really need to know is the mass in the case where your complete manifold is Ricci flat, and then it's practically trivial. Right? So anyway, so it's reduced to a much easier case. Okay. So that's n equals 4. So let me now move on to an application. Sticking with 4 dimensions. So this was what I want to talk about is one of the first geometric results in this field, but it's still a good one to talk about in this kind of setting because using the machinery we've set up so far, you can basically see what the essential idea is behind it, what estimate, the key estimate you need to prove, and why it works. But also, subsequently, there's been a number of results that use similar kinds of ideas. So there's sort of a general class of results that prove curvature pinching. So curvature pinching via fully nonlinear equations. So this is sort of the first result in that direction. Okay, so let me state the result, and then I'll sketch out the proof. So theorem is the following. So first of all, this was done with Alice Chang and Paul Yang, but the proof I'm going to discuss is basically due to some work I did with Jeff Yaklowski. Because it fits more in with, this is much before this one, so this one took advantage of a lot of the estimates and results that were developed in the interim. So the result says the following. So assume that you have a manifold, so M4, again, closed Riemannian manifold, whose scalar curvature is non-negative, and such that the integral of sigma 2, so this conformally invariant number, is positive. Okay. Then there exists a conformal metric, g hat, such that this holds pointwise. All right. Such that, so g hat is 2 admissible. So i.e., you go from the integral of sigma 2 positive in an integral sense to positive in a pointwise sense. So i.e., the Schouten tensor for this metric is positive, and the scalar curvature is positive. Okay. So in particular, what this implies is that the Ricci tensor of this conformal metric is positive, and it's pinched by the scalar curvature. So less than 1/2 the scalar curvature times the metric. Okay. So what you can compare this to, what this is sort of intended to generalize is the very classical result for surfaces, right? So in 2 dimensions, the analogous result would be to look at the Gauss curvature. So suppose the total Gauss curvature is positive. All right. Well, then, of course, you're conformal to the sphere. So the point is that, in fact, there's a conformal metric of constant positive curvature. But in particular, there exists a conformal metric with positive curvature. All right. So average Gauss curvature in an integral sense implies average Gauss curvature in a pointwise sense. And this is intended to generalize that result. Okay. All right. And then with all the machinery we have set up, we can reduce the theorem really down to one estimate. So let me explain that. So just a sketch here. But the essential ideas are already contained in a lot of what we've done. So let's just assume that in fact the scalar curvature is strictly positive. Okay. So if it's non-negative, then I can conformally change to make it strictly positive or scalar flat. But if it's scalar flat, then if you play around with the inequality we did up there, you can see that the integral of sigma 2 can't be positive. Okay. So I stated it this way, but it turns out you may as well just worry about this case. All right. So suppose the scalar curvature is strictly positive. All right, so that means the trace of the Schouten tensor for our metric is strictly positive. Then what you can do is the following. Look, if we knew that the Schouten tensor of this metric G were admissible, that is to say, if sigma 2 of this were positive, then we'd be done. I mean, that's what we're trying to show, that all we know right now is that the integral of sigma 2 is positive in average sense. If we knew it were positive in a pointwise sense, there'd be nothing to do. Okay, but we only know positive in an average sense. But we can do the following. If we take the Schouten tensor and we add a large positive multiple of the trace of the Schouten tensor, this is a positive number, right? So if T naught is large enough, the resulting tensor here will be positive. So there exists a T naught, maybe quite large, such that this is positive. So what we're going to do is view this as an initial metric and look at this condition and basically begin to deform it. All right, so let me explain a little more carefully. So let's let f of x be the square root of sigma 2 of a plus t naught times sigma 1 ag. This is a positive. This is positive definite, so if I take sigma 2 of it, I get a positive number, right? Positive function. And we're going to consider the following equation. Okay, so consider the following. It's going to be a one-parameter family of equations. All right. So sigma 2 square root of a plus, all right, it's a little bit complicated, so give me a second to write it down, and I'll explain exactly what's going on. It becomes clear if you write it the correct way. Plus t sigma 1 a is equal to f of x times e to the tu. So what's going on here is that, so i.e., what I'm doing here is I'm taking this sigma 2 of the conformal Schouten tensor plus a parameter t times the trace of the conformal Schouten tensor times g hat. And I'm setting that equal to f, this function f I've defined over there, times e to the tu. E to the 2u. And let's call this equation star t. Okay, it's a big mess, but let's take it apart in a couple different steps here, and you can see what the idea is. So, a couple notes. So, if you take t to be this number t naught I defined over here, now plug in u equals 0. All right. If I plug in u equals 0, then I have square root of sigma 2 of a plus t naught sigma 1 g equals f. Well, that's exactly how f is defined. So in other words, if t equals t naught, then u equal to 0 is a solution. Okay. Now, on the other hand, if I can solve this equation when t equals 0, right? If I can solve it when t equals 0, this term drops altogether, and what I'm just solving is the square root of the sigma 2 of the conformal Schouten tensor equals this positive quantity. So if t equals 0, the equation is just square root of sigma 2 of the conformal Schouten tensor is equal to f of x e to the tu. So now, but I need to add a little comment here. I could have this, but maybe a hat would not be admissible, but that you can rule that out pretty quickly. So if I have a solution of this, all right, then you can quickly see that that the scalar curvature has to be positive. It's just Cauchy-Schwarz, and so very quickly it has to be admissible. All right. So in any case, the point is that I'm beginning with I have a one-parameter family of solutions. When t equals t naught, I already set things up so that I have a solution. When t equals 0, I'd like to prove that I have a solution. So what we're going to do is use the continuity method. We're going to show that the set of values of t between 0 and t naught, all right, the set of values of t in this interval for which we have a solution, an admissible solution, is both open and closed, and therefore we have a solution for all values of t. So the idea, show that the set S of all values of t in the interval between 0 and t naught such that star t admits a solution, an admissible solution. I want to show that this set is open and closed. And if we can do so, it must be the entire interval. So in particular, we can solve it for t equals 0. Okay, so the open part is just the tedious calculation, but pretty straightforward. But there's something important to point out before. I mean, I won't actually do the calculation, but I'll just point out what's going on. But let me make an important remark here. So there's so many symbols here. It's easy to have all these equations look the same. But I want to point out here the exponential term. So the equations we've been talking about up till now, the exponential on the right-hand side is e to the minus 2u. When you consider the cone equation, this is the correct weight. All right. So we intentionally change the sign here to a plus. Okay. All we're trying to do is get a function u whose Schouten tensor lies in the correct cone. We just want to make sure that this quantity is positive. We don't really care what how you prescribe that positive quantity. Okay. So on the other hand, if you put the plus here, then this equation looks like, I mean, ignoring the gradient terms, it looks a lot like the negative cone equation. Right. The gradient terms are completely different, but I mean in that respect. And if you recall last week when I talked about the negative cone equation, the one advantage you had there is pointwise estimates for u were much easier. Okay, so that's one advantage to putting a plus here instead of a minus here. And the other advantage is when proving that the linearized equation is invertible, and therefore this set S is open. Okay, so let me see. No, it's not quite that easy, but I'll explain what I mean in a minute. But I just wanted to point out that the exponential term is definitely different, and for a couple good reasons. So, so note the exponential term. Has a different sign. From the exponential term and star plus, the equation we talked about up till now. Okay, so let me just say openness is pretty straightforward. You just calculate And the positivity of that exponent is crucial for openness, for showing that the linearized operator is invertible. But in any case, it works out. So openness, that two N's. That's easy to check. Say closedness. This is just reduces to a priori estimates, right? Okay, so let's go through the drill. Now, look, this equation looks different from the sigma k curvature equations, but at the level of estimates and many other things, it's essentially the same idea. So, taking into account some differences in structure, the ideas are basically the same. So let me first talk about pointwise bounds. So the first claim is that if U is a solution to star T, then the max of U has a fixed upper bound, all right, independent of T. Okay, this is just the maximum principle. So in the argument, I won't go through details, but it's just like the argument we did for the negative cone equation. So let me just point out the basic idea. Kind of up here. So you write down, so the proof for the claim, you write down the equation. The equation is, let me reverse the two sides. So suppose U at the point x naught is where U attains its maximum. Then you plug this point into the equation. You get this. So this is square root of sigma 2 of conformal Schouten tensor plus TE, blah, 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 right? Conformal Schouten tensor plus a multiple of its trace. Now we're just going to use this inequality that bounds sigma 2 by sigma 1 squared. In other words, Cauchy-Schwarz, or the geometric arithmetic mean inequality, however you want to think about it. So it's less than or equal to some sharp constant times sigma 1 of A hat plus T sigma 1 hat G hat. So this is really just Cauchy-Schwarz is all I'm using here. So you're just taking a trace of this. Well, if you take the trace of this and this check, what you get is the trace of the background Schouten tensor. I guess there's some constant. Yeah, well, you just change the constant here. And then plus, what is it? You get like Laplace U here, and then minus some other constant times grad U squared. So I'm dropping all the constants, but it doesn't really matter. So, and you're evaluating this at this point x naught. Okay, but this is a maximum point, so the gradient terms are gone anyway, so it doesn't matter. And at the maximum point, this is less than or equal to 0, so I can just drop that point. So what I get is an upper bound on U. Okay. So again, that's why we put a plus here and not a minus here. If I had a minus here, it would tell me nothing about the maximum point, but now it does. So U is bounded above. Now you go back to the local estimates, and as I said before, all right, the equation's different than the sigma k equations, but in a very straightforward way. So you can just trace through the proofs of the local estimates and just verify the same kind of arguments work. And what you get is the same kind of derivative bounds in terms of C0 information. So a little more precisely, what you get is that the maximum, we don't need to localize this, just do it globally. The maximum, say the gradient plus the Hessian, is bounded by, so the maximum of 1 plus, okay, the usual form of the local estimates, you have an e to the minus 2u over here, but because we switched the sign on the right-hand side, it switches here in the expression for the local estimates, so you get this. And this is great because we already know that u is bounded above, right? So this term is now bounded above. So now we have uniform control on the gradient and the Hessian of u. Okay. So this just follows from the usual local estimates. Okay, now we're in great shape. We just have one thing to check. All right, and it's again a lower bound. So what we worry about is u is bounded above, but if at the minimum point u goes down to minus infinity, say as t approaches 0, for example, then because we have bounds on the gradient, what will happen is u uniformly will crash down to minus infinity. All right, so that's what we have to worry about. A sequence of solutions, say for a sequence of values of t, for which u goes to minus infinity uniformly. So can we avoid uniformly? Now, so far we haven't used anything, right? I mean, we just said if you take any metric of positive scalar curvature, I can do this, right? I take any metric of positive scalar curvature, I can take the Schouten tensor, and if I had a large multiple of the scalar curvature times the metric, I can make this quantity positive. I can write down this family of equations. The linearized equation will be invertible. I can get the estimates in claim 1 and claim 2. So so far, I haven't really used anything at all other than positivity of the scalar curvature. So in general, no, you shouldn't be able to avoid this because it's not true that if I just begin with a metric of positive scalar curvature, I can always deform it to one whose sigma 2 curvature is positive. There's going to be obstructions, right? Sigma 2 curvature positive in 4 dimensions, for example, implies positive Ricci. Well, there's a lot of manifolds that admit a metric of positive scalar curvature, but not a metric of positive Ricci curvature. So you have to use something global that rules out this possibility, right? Otherwise, this could clearly happen, that everything just crashes to minus infinity. If I write this down in an arbitrary manifold of positive scalar curvature, this is almost certainly going to happen. Okay. So how do we avoid it? We have to use this assumption, obviously, on the integral of sigma 2. That's our global piece of information that we're going to use. And how do you use it? Well, what you do is you write down the condition on sigma 2. So let me state this as a claim. So claim, I guess, 3. The integral of e to the 4u is bounded below by some positive constant times the integral of sigma 2. So therefore, if this is positive, I get a uniform lower bound on this integral. And a uniform lower bound on this integral certainly prevents u from crashing to minus infinity uniformly. Right? Okay, so this is the key estimate. And this follows just by using the equation and just some algebra. So what you do, so the proof is, so our equation involves sigma 2 of this tensor, right? Conformal Schouten tensor plus some multiple of the trace times the identity. Well, you just expand this out, right? I mean, you can just write down sigma 2 of a matrix plus some multiple of the trace. You can just write out. You get sigma 2 of a hat plus some constant. I'll tell you what it is. It's 3t 1 plus 2t, happens to be, times sigma 1 of a hat squared dv hat. So this term is always non-negative, right? So I can just throw it away. And this is conformally invariant, right? So this is equal to sigma 2 of a for the background metric. Again, conformal invariance coming in. And we're assuming that's positive. So the integral of the left-hand side of our equation is always positive. But if you use the equation itself, this is exactly f squared times e to the 4u. Right. After you rewrite the volume form and use the equation, you get this. So this just tells you that the integral of e to the 4u is bounded below by some constant times the integral of sigma 2. So you get this. All right, so that rules out everything crashing to minus infinity, and that gives you, so claims 1 through 4 implies there exists a solution u naught of your equation with t equals 0. And when t equals 0, you're just saying that the sigma 2 of the conformal Schouten tensor is positive, which is what's claimed. Okay, so QED. Okay, let me just finish up by making a couple remarks and then I'm all done. So just to say that this technique, I mentioned that it's the first in several examples of proving kind of curvature pinching results using these fully nonlinear equations. So this has also been used by Weimin Sheng and also more recently by Catino and Jadley. The setup is essentially the same. You begin with some conformally invariant assumption. So here was the integral of sigma 2, and these works, it's some different conformal invariant. You take the Schouten tensor and add some multiple of the metric, and then you write down your deformation equation, and then what it boils down to is you set things up so that at some point one of your one-sided C0 bounds depend upon the positivity of some conformal invariant. And if you can do that, then you can deform from a weaker curvature condition to a stronger curvature condition. All right. So there's been some other results that are very much along the same line. Okay. I got through quicker than I thought I would today. So, okay, thank you.